Professor Zhang is not available today, so I'm happy to be your host for this week colloquium. Okay, so today's speaker, Professor Hsiung, is very famous, so everybody knows in this room. But to be a formal the event, I'd like to briefly introduce him. The Professor Hsiung received his bachelor's degree at NTU Physics Department and got his PhD in Columbia University. He has been working on experiments of discovering direct CP violation in neutral kaon decays and rare kaons and B-meson decays. Also, he has been working for LHC, the CMS experiment, to search for new physics for many years. And also, he has been working for the diabase Neutrino Oscillation experiment, discovering third mixing angle, which is related to today's topic. And he was the co-spokesperson of the KTEV experiment at Fermilab before he returned to NTU in 2002. Okay, and he received the Outstanding Scholar Award from the Foundation for the Advance of the Outstanding Scholarship. Oh my God, it's a long award. And he was the physics department chair up to the last year. Also, the president of PSC ROC. Actually, I got noticed that it's kind of great news. He recently has received the National Professorship of Taiwan from Ministry of Education. Okay, so let's congratulate him also. Let's give a warm welcome to him. Okay, thank you.
Okay, thanks Jim's introduction, and I think this time I think I would like to introduce the smallest particle in particle physics, and also it's one of the mysterious one, and it's a neutrino. Sometimes I think we call it Weizongzi, or in China I think called Zhongweizi. So anyway, so that's my talk title, Elusive Neutrinos, and I'm going to cover the neutrino oscillation, phenomena, mixing, and the mass hierarchy. So the first, okay, what is a neutrino? Okay, if we try to quote, from the Ryan's and Cohen in 1956, okay, they discovered first neutrino events, and it's nothing, almost nothing. And that's what it's saying. The most tiny quantity of reality ever imagined by a human being, and also despite that, okay, this particle never ceased to question physicists and to give headaches to the one who wants to detect it. In many years, okay, you can see since 1956, the neutrino physics actually become a bigger field, and we actually start learning, okay, more and more its properties, and they're also a surprise. So the first discovery actually in 1956, the experiment, and the size is like this. You can see the detector, and it's sitting next to the reactor. Okay, nuclear power plant reactor. Then you can see the neutrino coming from the reactors. The neutron decays. Then they come in toward here. Then it will make some interaction. And this is the weak direction. So you can see it's the anti-neutrino, electron type anti-neutrino, and it reacts with the proton and make a positron and the neutrons. Okay, this is probably the only, the reactions. We know how to use. Yep. No reason. I think in there, somehow when they quote, they use it.
Really?
Yes. Okay, so of course the neutrino was postulated by Pauli in 1932-1933. You can see this is the conference in Brussels. The Pauli says, okay, their mass cannot be very much more than the electron mass in order to distinguish them from the heavy neutrons. Mr. Fermi has proposed to name them neutrinos. So the enos means small, okay, tiny, and the neutrino. So it's actually the things borrowed from the neutron, okay. So it is possible that the proper mass of neutrino be 0, and it seems to me possible that neutrino have a spin 1/2. We know nothing about the interaction of neutrino with the other particles of matter and with photon, at least that time, okay. The hypothesis that they have a magnetic moment seems to me not founded at all, okay. So anyway, this is even before, we understand so-called weak interaction. And neutrino at that time, basically come from the so-called nuclear beta decay, from neutron decay. So this is the picture you can see. The neutron of the nucleus decay into the proton, the electrons, and the neutrino, or the inverse beta decay. Off. Does it work? No? Oh, it works now. So, okay, so you can see the if it's a proton, it actually can also transform into a neutron, and also making the positron and also neutrino. So there's a 2 types actually. From here you say neutrino and anti-neutrino. So since then, of course, it took many years from 1932 to 1956. It's the first discovery of the neutrino events was detected at that time, and it's using this, as I said, the inverse beta decay, the anti-neutrino of electron type plus proton make a positron and neutron. Then these two signal. The positron will annihilate with the electron basically right away. We call the prompt signals. Usually it will be detected by the scintillator, making 2 gammas. And the neutrons is a delay signal. It's going to wander around, okay? And it takes some time to be absorbed. Then depending on what kind of material you use a cadmium to capture this neutron, then it will be 8 MeV delayed photons will be detected. So this actually Feynman, okay, everybody knows Richard Feynman, okay, make a joke of this. So all you have to do is imagine something that does practically nothing. That's how he described neutrino. You can use your son-in-law as a prototype. So, also, like your son-in-law, they change form when you are not looking. Okay. All right. So this is the photo of the experiment at the time, and to do the experiment, of course, you have to, the physics has to come in. So basically, the neutrino from reactor, just from the neutron decay, you can estimate the so-called flux versus the energy. You can see it's coming down this way. The higher the energy, actually smaller the number. But the neutrino has a very peculiar property. The cross-section for the neutrino at this low energy is rising. Basically almost linear with the energy. So you can see it's rising this way. So the expected signal will peak like this. So this is the 1 MeV to 60 MeV region. You can see it can be estimated. So in 1959, they published in Physics Review. You can see their data. So the data is like this, and this is the prediction. So you can see the data almost, of course the error bars are actually large. You can see they only plotted 2 error bars here, and but the shape is sort of consistent with this shape. So they won the Nobel Prize in 1995. Right round. So based on this, okay, even we found the first, neutrino type events. So what we know about neutrino are weird, okay, and they're neutral. They're basically speed 1/2. We call it the fundamental particle. Looks like probably it's a point-like particle. Only appear in the weak direction, so very hard to detect. Okay, the usual, strong interaction, EM interaction, they don't participate. Very tiny mass, but not massless. That's what we know now. Okay, and the upper limit right now is probably at 2.2 eV. However, okay, the neutrino might hold a key to the universe because it's one of those things. It's just too cool to be an accident. If they, they can exist, and in such weird, weird form. So since then, actually, there are more and more properties, as I said, okay, discovered, and also that's one of my the main topics today. Anyway, neutrino have a small mass. The small mass, how does it come from? Okay, in the current standard model, actually, there's no real good, there's one possible model in theory to explain, but we have not actually found good evidence for it yet. But anyway, you can see the neutrino. If this is the mass scale of all the standard model type particles, and we can see the grand unification theory usually will predict something around up to 10 to the 16, but all the masses is below, about 200 GeV. So WZs and Higgs, the ordinary particles, like the top actually up here, and then all the other quarks and leptons and trinos, just very small. Okay, so there's also, okay, in the grand unification theory, we sort of right now has the expectation, all the forces might unify at some point, which you can see it's around, say 10 to the 15 or 10 to 16 GeV level. Of course, this is a model, this is a theory, and to get small mass, one of the models is the seesaw mechanism. The seesaw mechanism actually using the this kind of assumption. You see of this matrix, and you can see the this matrix. If you have a small m, which is off diagonal, and on the diagonal you have a 0 and big M. Big M is 10 to the 16 GeV, and the small m is 10 to the about 100 GeV level. Then once you diagonalize, you will get the m squared over m. Okay, then this is time. This is about 10 to the minus 3 eV. This might explain the neutrino mass. Of course, we still don't know what is the neutrino mass. What's the real mass? So this is only one of the possible explanations. Then since 1956, actually a couple years later, the Leatherman, Schwartz, and Steinberg actually using the accelerator at Brookhaven National Lab in Long Island, and that time they actually can, extract some neutrino beam along, toward their experiment. The experiment actually has a lot of shielding. You can see. Then they put their detector somewhere in the cave, okay? And it's using actually the detector right now. We probably nobody use it. It's called spark chamber, And so it counts the number of sparks. And there are two kinds, actually, the distribution you can see. One is there are a lot of, the so-called sparks. The other one has a smaller. So these two actually looks different. One actually is, these are probably like we call electron type. So the neutrino actually, the other one is called muon type. Okay. So the neutrino, the two-type neutrino coming out of this, and somehow, okay, it converted, and they make interactions. Then, so the very weak, so-called weak interactions. But somehow the electron type convert into electron, muon type convert to muons. So this also got their Nobel Prize in 1988. Of course, after that, we sort of found at least some way to measure the so-called neutrinos. Then Ray Davis actually since around 1970s. He's using the so-called chemical reaction, chemical extraction method to extract out the some rare, interactions from this big tank. So this is the way actually he believes, okay, to measure the neutrino from out of the sun. Okay, so we have, the sun which is burning its fuel. And of course, during the burning, and it actually making the so-called neutrinos, and just like the so-called nuclear, reactions, like beta decays. So these neutrinos come from the sun, and they got absorbed inside this tank, and he tried to extract out, every month. So you can see this is from 1970 all the way to this is like 1995, and the average compared with the expectation, there's a really big difference. Even though the error bar you can see is really big, there also seems to have some cycle of the like the sun, the 11-year cycle of the sun, spot. But anyway, the this difference, okay. Basically, what right now we think is due to the neutrino oscillation, and some neutrino from the sun are missing. Okay, so in 2002, he was awarded also the Nobel Prize with the COSHIBA, okay, who pioneering the contribution to astrophysics, in particularly on detection of cosmic neutrinos. Anyway, so of course, takes many years to really understand, this is so-called the solar neutrino problem, and the solar neutrino actually with many different experiments. This actually makes it more clear. You can see the theory predictions, so-called the standard solar model, and it's up here. And the different, experiment, they all shows, there's a deficit. Okay. And when the snow experiment actually was mounted in the Canada, and it actually being able to measure, at least all three types, the sun. And then you will see, okay, even though the electron type neutrino is missing from the sun, but all three types, they do sort of agree with the expectation. So this is the one of the really great evidence about the neutrino oscillation. Of course, the idea of oscillation. Okay, the idea of oscillation actually already exists quite some time ago. In 1957, Ponticolo actually was proposing a process called the Neutrino Oscillation, and please, still doesn't come out. It's even worse. Oh, where? It's not stable. have to press very hard. Okay. Change another one. So the laser point is never reliable. So initially he proposed actually is the neutrino change to anti-neutrino, so-called nu L goes to nu L bar. But later, after the so the second so the mu neutrinos discovered, he proposed the nu E to nu mu. That time we only knew two forms of neutrinos. So of course, you know, nobody take it serious at that time. And even though it is okay possible, but it takes okay almost more than a decade to really measure the so-called this phenomenon. But the phenomenon actually when you simplify actually quite simple. So basically this is nu x after going through some distance and travel some distance, then will remain as a nu x. And this probability, actually, you can use the, I will show you later, actually, the two flavor ones, and using the quantum mechanics easily to extract out. You will find out, okay, it's 1 minus, okay, total probability 100% minus this term. This term actually has a coefficient we call the sine squared 2 theta xy, okay, this is the amplitude, how large the oscillation. And the other one is the second one, the sine squared, 1.27 times the delta m squared times L over E. L over E, distance divided by energy. This is time, okay? So you can see this is really oscillating with the time, okay? If the mass difference is squared between these two species, they're non-zero, okay? If this is zero, there's no oscillation. So anyway, so you can see the with the unit of the L in meter, the energy in MeV, then the delta M squared in EV squared, then this has a coefficient 1.27 conversion. Okay, so this is a very simple formula, and we will see later. Okay, we do see such kind of oscillation. So the story actually goes, yeah, we don't really have only two types of neutrino. We have three, and the three types of neutrinos actually was first in basically using the E plus minus, the collider at CERN. There are 4 experiments try to measure so-called the Z width, the Z boson width. From the Z boson width, the line shape, you can clearly fit. And you will find out, okay, the 3 neutrino type fits very well this width, and it's different from the 4 and different from the 2. So the third type of neutrino actually associated with the tau. In 1977, we also discovered the tau, and later, I think, much later, I think we also found some events of the so-called the tau neutrino events. So this complete so-called the standard model with 3 generations, quarks and leptons, and then we also have the force carriers for the EM interaction, strong interaction, weak interaction, and now, okay, just the 2012, we also found out the so-called there's a Higgs boson, okay, in this table. So the neutrino oscillation actually not only can come from the sun, and basically if you have neutrino source, then basically for example from the upper atmosphere, okay, there's air shower, the so-called hitting the upper nucleus of the atmosphere, then generates like pions. Pion will decay to muon, muon decay to electrons and also neutrinos. So these neutrinos from the upper, atmosphere, they can also, coming down toward the detector, say, in the ground, then you will also see the oscillation. This is one of the example. Okay, this is in the super K, and the cosine theta actually is the so-called the zenith angle, and you will see actually the expectation and also the data. Clearly see there is something missing. Okay. So it really is a neutrino oscillation. This is using another experiment called Camelan. The Camelan actually is also in Japan, which is it's about 100 to 200 kilometers away from several nuclear power plant reactors. And by accumulating many years data, actually you can see this is the same thing. We plot so-called L over E. Okay, this is the time, and you clearly see there is oscillation curve, and this is a very very strong evidence. This so-called survival probability. And if you look at their so-called energy spectrum, you remember it's supposed to peak here. Actually, it doesn't peak that well. So there's also deficit over here. So this is the several the so-called reactor the neutrino experiment, including the so-called accelerator type experiment, and we have this time the so-called delta m squared versus the tangent square theta plot. Okay, and still there are a lot of the regions ruled out, but basically right now supports so-called the nu mu to nu tau oscillation and nu e to nu mu to nu tau oscillations. And so basically neutrino are not massless. We found, at least that time, the evidence for neutrino flavor conversions, and the experimental result shows neutrino does oscillate. Except, the most of the oscillation actually is between the three flavors here, only between two of them, and so there's supposed to be the third mixing angle. So I will, before I actually introduce so-called the third mixing angle, I can show you the so-called, this is a very large super Kamiokande detector, in the water, and I think the cave and this building can basically sit in there, set a cave. So then when they fix the detector, they have to use the boat. So let me describe so-called neutrino oscillation in vacuum. The oscillation actually not only can generate in vacuum, actually when you go through the matter, it can also have oscillation. But let's simplify it. So the neutrino, since as I said, they have a very tiny mass. That means their mass is actually very close. So generally, they have different flavor. So their flavors is related to so-called interaction or the weak acting state. It's different from their energy, so-called mass acting state. And in the two flavor situation, and basically you can just use this matrix using one, the mixing angle. You can actually rotate this nu1, nu2 mass acting state into this flavor acting state. Then when you start with the 1, the pure nu e, then after some time you can see star oscillates, and the same thing will be the other one. So basically you will, if the experiment can really measure this well, then you will see this oscillation pattern. So this shows up the nu1, nu2 are very close, the masses, and also this shows some difference, the fractions of the so nu e with this kind of mixing, so you call the mixing angles, mixing matrix, how much actually is nu1, how much is nu2. So the two flavor oscillation, you try to calculate so-called electron to muons oscillation, or you can calculate one